Okay, guys, this is a Hess's law problem. Hess's law, this is another way to find the overall energy change in a reaction. We learned how to use the enthalpy change. If they give you the mass and then they give you the overall delta H, we can use a balanced equation to find the overall delta H for a reaction. This is another method. Most chemical reactions occur in multi-step processes. So that's what this is showing here. It's showing you that this overall process is actually not as simple as it looks. You look at it and you say, okay, carbon plus half an O2 molecule yields carbon monoxide. Seems simple enough. Most reactions, though, occur in multiple steps. So remember, when a chemical reaction is taking place, atoms break apart, new bonds form, and this process doesn't always occur in one simple step. And in fact, most of the time, it does not occur in one simple step. It occurs in multiple steps. So that's what these are. These two that they're showing you up here, these two multi-step reactions can be rearranged to achieve this one overall reaction. So it's kind of like a puzzle. Here's my suggestion about how to go about this. The goal is to rearrange these equations up here into a format that looks like this. And that means we need to have all the reactants on the correct side, all the products on the correct side, and we need to make sure the coefficients are the same. Here are the rules for doing this. Okay, there are really only two things you can do. You can multiply an equation by a number, which changes its coefficient. The other thing you can do, you can reverse a reaction. So for the first one, when you multiply an equation by a number, you have to, whatever you do to the equation that changes the coefficients of all the substances in that equation, you also have to do that to the delta H value. If you reverse a reaction, you have to change the sign of delta H from positive to negative. Okay, so whatever you do to the equation has to be reflected in these delta H values right here. Okay, so if I were to, for example, we may not have to do this, but I'm just going to show you an example. If I were to multiply this entire equation by 2, then I would need to multiply this delta H value over here by 2, because the goal is to obtain the overall delta H for this reaction. So whatever we do to the equation, we need to do to the delta H, which will then reflect an accurate, well, will give you an accurate reflection of what the overall delta H is for that particular reaction. Now, I know this may sound like totally foreign and like, what are you talking about? Why would I even need to multiply these equations? Why would I even need to, do any of the stuff you're talking about? So let's work through this one together and then you'll see what I'm saying, hopefully. Okay, so I would start out like this. You look at carbon. Carbon is a reactant in this overall equation, and it has a coefficient of 1. Those are the two important things. We come up to our two equations, and we locate carbon. Carbon is also listed as a reactant up here, and the coefficient's 1. So we don't need to do anything to this equation at this point. Now I'm going to go on. O2. O2 appears 2 times up here. It appears right here, and it appears right here. Anytime you run into that situation, I would skip over that one and go on to the next thing in the equation, because by doing that, the oxygens are probably going to fall into place. So let's look at where the carbon monoxide is. Carbon monoxide is a product here, and it has a coefficient of 1. Carbon monoxide is a reactant up here, and it has a coefficient of 1. So the coefficients are fine. However, the carbon dioxide is not on the correct side of the equation. So what we're going to have to do to this is reverse this equation. So these now become the reactants, and these now become the products. And since we reverse this equation, whatever we do to the equation, we have to do to the delta H. So I'm going to change this delta H from a negative to a positive. Okay. So if you're confident in what you've done and you're like, okay, I think I've done the right thing, at this point, you just have to add these two things together and it will give you the overall delta H for that reaction. So when I add those two together, I get negative 110.5 kilojoules. And that is my answer. So all that work for that little answer. If you're not sure, if you're like, I don't even understand what you just did, how do I know that I did it correctly? Here's how we can confirm that we did this correctly. I'm going to take all the reactants from these reactions up here, and I'm going to add them together. So I'm going to take my solid carbon plus my O2 gas. Okay, so I've taken both of these reactants, and then I need to take this as a reactant because remember I reversed this reaction. So I'm going to put plus CO2, and that's a gas, yields all the products. CO2 is a product right here, so I'm going to write that. And carbon monoxide is a product, so I'm going to write that here. And then 1/2 O2 is also a product. So what I did is I just rewrote all the reactants and products. And the goal is it should cancel, everything should cancel to look like this equation if we did the right thing. Okay, so carbon cannot cancel. Carbon is staying. There's nothing for it to cancel with on the other side. Now we need to take a look at oxygen. I have an oxygen here, and I have a half an oxygen over here. All right, so now I need to, it's kind of like simplifying an algebraic equation. I'm going to subtract 0.5 oxygens from this side and subtract 0.5 oxygens from this side. When I do that, I get half an oxygen left on this side, and the rest cancels out. Okay, so we're done with oxygen. CO2, I have a CO2 over here, I have a CO2 over here, cancels. So that takes care of the reactants. Now all that's left on the product side is carbon monoxide gas. Now I look up to my original equation. Are they the same? Yes. Yay. 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 It's the same. So what that means is what I've done over here to these delta H values by reversing that reaction and adding those two together, this is the correct answer for the delta H for this overall reaction. Now I know it's a lot of work for one little number, and eventually you'll get to the point where you're comfortable with, okay, I've done the right things to the equations, I know it's right, I don't need to do this confirmation step down here because that's really what's time consuming, not the adding the delta H values together. So Hess's law, another way to find the delta H of a reaction.